Over 799.
Derivatives of trig functions, lesson 2.
Oh, yeah.
You're just going to have to wait a little minute. Go in that room over there. That's okay.
Ben, you want to make guesses on who that was? Yeah. It sounded like Evan.
Was it?
Sounded like his Duramax. That's Durex.
Oh.
Duramax is the diesel brand for GM vehicles.
Why would you get a GM? What does that even stand for? Grand Master?
General Motors.
Are they trying to be General Motors?
It drives actually a GMC, a General Motor company. A GMT, a General Motors truck.
It's crazy. You know what I drive? Honda.
There you go.
Yeah.
Yeah, I got that American steam in my car.
Okay, so remember what the graphs of sine and cosine look like. They are drawn there. So you can tell by looking at the graph that the limit as theta approaches 0 of sine theta would be 0. Remember, the limit is asking what is the value of y approaching, as in this case x gets closer and closer to 0, or theta gets closer and closer to 0. So you're approaching that point right there. You're approaching the point 0, 0. So that's why that's the limit. However, the limit as theta approaches 0 of cos theta is 1, because as theta gets closer to 0, the graph is approaching this point that has a y value of 1. What if we wanted to know the limit as theta approaches 0 of sine theta over theta? So we could do this, or guess what this is, by using a table of values. If we approach 0 from the right side, meaning the values of theta are positive, you can see that sine theta over theta is approaching a value of 1. Right? So to do this, you'd have your calculator in radian mode. When theta is 2, you take the sine of 2 divided by 2, you'll get 0.45. The sine of 1 divided by 1 is 0.84, and so on. So as theta approaches 0 from the right side, sine theta over theta looks like it's approaching a value of positive 1. And as it's approaching theta from the left side, the same thing is happening. It's approaching a value of positive 1. So the limit as theta approaches 0 of sine theta over theta is 1. Now remember, theta or 0 is a non-permissive value, right? So you can't find out what it is by letting theta equal 0, because that would give you the denominator of 0. So a limit would be used to determine what the value of that limit is. So also remember that the limit as x approaches a of c times f at x, because c is a constant, it can come in front, and that equals c times the limit as x approaches a of f at x. So using that law, as well as the fact that the limit as theta approaches 0 of sine theta over theta equals 1, we can evaluate these limits. Okay, so the first one is the limit as x approaches 0 of sine x over 2x. Again, 0 is a non-permissive value. If you let x equal 0, you'll have a denominator of 0, which we can't have. So what we want to do is we want to take this expression and we want to do some work to it, some algebraic processes or steps, so that we get a term or a factor that has the limit as theta approaches 0 of sine theta over theta. Because if we can get that factor, that part equals 1. So this is how this first one would be done. This 2 is like a coefficient of 1/2. This is the same thing as the limit as x approaches 0 of 1/2 sine x over x. You see, if you multiply those together, top times top, bottom times bottom, you're going to get sine x over 2x. So now that 1/2 becomes a constant, it can come in front of the limit. So it'll be 1/2 times the limit as x approaches 0 of sine x over x, which we know that part is 1. So now we get 1/2 times 1, which is 1/2. So there's the value of that limit. Okay, looking at number 2. We want to find the limit as x approaches 0 of sine 2x over x, right? Again, 0 is a non-permissive value. It cannot be found by just straight substitution. But remember, we know that the limit as x approaches 0 of sine x over x is 1. And the key here is that the argument of the sine has to equal the denominator, right? In our general expression, they're both x. But in reality, they can be anything as long as they're the same value. So if we want to find the limit as x approaches 0 of sine 2x over x, because the argument of the sine is 2x, we have to have a 2 on the bottom as well to make it 2x. And that can be done by multiplying top and bottom by 2. So now we'll take a limit as x approaches 0 of 2 sine 2x over 2x. Again, I multiply top and bottom by 2. And then the 2 on top, the factor of 2 on top will come in front. So it'll be 2 times the limit as x approaches 0 of sine 2x over 2x. And that part is 1. So this will be 2 times 1 or 2. So there's the answer. That's the value of that limit. The argument and the denominator have to be the same. Number 3. We have sine 7x on top, sine 4x on the bottom. So again, we've got to do some work. So what we would do as an initial step is rewrite this as the limit as x approaches 0 of sine 7x over 1, all divided by sine 4x over 1. Remember, we need to have the same denominator as the argument. So I'm going to take this top part, the limit as x approaches 0 of. The top part, I will multiply top and bottom by 7x. So it's going to be 7x sine 7x over 1 times 7x. And the denominator, sine 4x over 1, I'm going to multiply top and bottom by 4x. And using the properties of limits, well, we're going to do two things here. I can write these as individual limits, so it'll be the limit as x approaches 0 of 7x sine 7x over 7x, all over the limit as x approaches 0 of 4x sine 4x over 4x. And so a couple things are going to happen here now. Number one, and we could have done this on the last step before we wrote this one down. These x's cancel. Okay, I can divide top and bottom by a factor of x, so those x's cancel. And I'm left with 7 over 4, which is a constant. And it'll be times the limit as x approaches 0 of sine 7x over 7x all divided by the limit as x approaches 0 of sine 4x over 4x. And then yes, it'll be 7 over 4 times 1 over 1, which is 7 over 4. So that's how that one is done. Okay, so again, in order to make these work, we have to get an expression where we have the limit as x approaches 0 of sine theta over theta, where theta has to be the same, obviously. Okay, so looking at, did I miss one? Nope. Yes, I did. I did. So let's copy that to a new page. So again, we need to get an expression that involves the limit as x approaches 0 of sine theta over theta. This one here is in terms of cosine, so we need to do some work on this to get it in terms of sine. And so what we'll do here is we're going to multiply top and bottom by the conjugate of cos x minus 1. That'll be cos x plus 1. This is one of the tricks that we did when we were proving identities. Sometimes we multiply top and bottom by a conjugate. So the reason this works is now we're going to have the limit as x approaches 0. When you multiply those out on top, you're going to get cos squared x minus 1. The front terms multiplied together gives you your cos squared x. The outer and inner cancel. The last terms, negative 1 times 1 is negative 1. And on the bottom, we'll have x times the cos of x plus 1, which I'm going to leave in factored form. I'm not going to multiply that out. Now, cos squared x minus 1, we can write that in terms of sine. And here's how. Again, we know from our Pythagorean identity that sine squared theta plus cos squared theta equals 1. So we can say that sine squared theta equals 1 minus cos squared theta. We've used that identity lots. 30-1 and now in 31. So if we take this last statement and multiply both sides by negative 1, negative sine squared theta would equal negative 1 plus cos squared theta, or cos squared theta minus 1. We can replace that cos squared theta minus 1 with negative sine squared theta. So this will be the limit as x approaches 0 of negative sine squared theta all over x bracket. And I guess I wrote theta. I need to fix that to an x, which I will. All right, so using the property of limits, that negative 1 in front of the sine squared theta can come in front of the expression. And now I've got the limit as x approaches 0. I'm going to split this expression into two parts, two factors. I'm going to take one of the sine squared x's, or one of the sine x's, I should say, and put it over the x, which is the first factor on the bottom, times the limit as x approaches 0 of the second sine x over the second factor on the bottom, which is cos x plus 1. So I've got negative 1. That second factor, the limit as x approaches 0 of sine x over x, is 1. And the third factor, we can actually evaluate. We can let x equal 0 to evaluate that, because 0 is not a non-permissive value. So it'll be times the sine of 0 over the cos of 0 plus 1. And if you look at 0 on the unit circle, the coordinates there are 1, 0. So the sine is 0, the cosine of 0 is 1. So it's going to be negative 1 times 1 times 0 over 0 plus 1. It doesn't really matter because that last factor is going to be 0. 0 over 1 is 0, and negative 1 times 0 is still 0. So there's the value of that limit. Right, so sometimes you got to use those tricks that we learned about in 30-1 and 31 when we solved trig equations or proved trig identities. So what's different about this one? Notice that it's a limit as x approaches pi. Again, it cannot be done by substitution, because when you let x equal pi on the bottom, you're going to get pi minus pi, which is 0. So here's what we're going to do for this one. We will say that as x approaches pi, x minus pi will approach 0, which is what we've talked about already. The denominator, the closer that x gets to pi, the closer the denominator will get to 0. So as x approaches pi, x minus pi will approach 0. And then also we can say that pi minus x will also approach 0. It doesn't matter if it's x minus pi or pi minus x, they will both approach 0. Also remember, we have our related angle identities. The sine of pi minus x is the sine of x. And that's on your formula sheet. And again, it comes from using the difference identity for sine and simplifying, you'll get sine of x. So we can rewrite this limit. We have the limit as x approaches pi of sine x over pi minus x. We can change it to the limit as pi minus x approaches 0 of sine of pi minus x, because again we know that the sine of pi minus x is equivalent to the sine of x from that related angle identity, and we can go backwards. The sine of x is also equal to the sine of pi minus x over pi minus x. And again, because we have this argument equaling the denominator, this is 1. That's the same as sine theta over theta. The limit is, it approaches 0, the limit as the denominator approaches 0 of sine theta over theta. So it equals 1. Right, so there's that one done. Number 6, the limit as a approaches 0 of sine squared 2a over sine squared 5a. So this would be the same thing as, in brackets, the limit as a approaches 0 of sine 2a over sine 5a all squared. That's what that means. And so we saw one similar to this before. Because the numerator is sine 2a, we'd have to have a 2a on the bottom, directly below that. And because the denominator is sine 5a, we would have to have 5a directly below that as well. So we can do that. We can do that by multiplying the top, sine 2a by 2a over 2a. And again, I'll break this up into individual limits like we did before. So we'll have 2a sine 2a over 2a all over the limit as a approaches 0 of 5a sine 5a over 5a, and that's all squared. So like we did before, the a's will cancel. So that 2 over 5 becomes a constant. Before we take it in front, in this case, we have to square it because it's all inside those big square brackets. Everything inside there is squared, including the 2 and the 5. So this will become 4 over 25 times 1 over 1, or 4 over 25. And incidentally, I mean, you can always check to make sure your answer is reasonable. You can take the original expression and you can choose values of a getting closer and closer to 0, right? To see if the answers you get is approaching 4 over 25. Because you square the 2 and the 5. Before you take it out in front as a coefficient, it's got to be squared first. Notice in this case, for number 7, it's not approaching 0. Plus the fact that there's no denominators there tells us that there aren't any non-permissive values. This one can be done just by substitution, by taking the cosine of pi on 4 and subtracting the sine of pi on 4. And those are both root 2 over 2. So we get an answer of 0 for that one. So number 8, again, our non-permissive value for this expression would be 0. X isn't approaching 0, it's approaching pi on 6. So it can be done just by straight substitution. The cosine of pi on 6 times 2 times pi on 6. The cosine of pi on 6, that's the first stop on the unit circle. That value is root 3 over 2. And that's divided by 2 pi on 6, which is pi on 3. We would do this by multiplying by the reciprocal. So it'll be 3 root 3 over 2 pi. Again, the non-permissive value for that is 0. We're not approaching 0, we're approaching pi on 6, so it can be done just by straight substitution. So you can work on those questions. I will post those to Google Classroom. So you can check your answers. Okay. And then Monday we'll start looking at the actual derivatives of trig functions.
Polymers are pretty easy. Just big 5 for 9. I know, but that's the stuff that was kind of useful. I studied Compton scattering all night because, well, I didn't understand it too well. It was, well, see, it was. it's still not a lot of. It's Charleston.
I was just like, and he said they passed right into this hospital. I thought it was
I wonder what.
yeah. And I'm playing fun basketball. Okay, so we started a soccer club back at Crystal Park. And it was like, and you just like, it was like beyond. This guy would like sliding tackle him, or just straight up running.
There's no ball, Graf. There's no ball.
There's no ball. Not so like 50 times bro. Yeah. 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 Obviously.
I really want to play quiz and
Oh yeah, back in grade 8 or 7 was the actual soccer.
yeah, but no, this is football.
Oh, football. Oh,
Football.
Um,
But we're playing, right? And like, I'm not gonna believe it.
yeah.
I never knew it. So I just like plowed through them with the ball. It's like, she says,
They say that for every girl sport. I'm like, no, it's just boys.
You guys should probably be practicing these, eh?
Yeah. Yeah.
Brighton,
See, that's the one.
you'll thank me.
I will.
I think you could try to like people should have.
Yeah.
Well, because every time I shit, I shit, I would go.
No. Yeah, shit. You just.